Ultrasonic spray nozzles atomize liquids using high-frequency mechanical vibration rather than high pressure. At the core of the technology is a piezoelectric transducer, which converts electrical energy into ultrasonic vibration. These vibrations propagate through a metal nozzle body and reach the atomizing surface at the tip. When liquid is delivered to this vibrating surface, the ultrasonic motion generates standing capillary waves in the thin liquid film. As the vibration amplitude increases, the peaks of these waves become unstable and eject tiny droplets from the surface, producing a fine mist. Unlike conventional spray nozzles that rely on high-pressure flow or compressed gas to break up the liquid stream, ultrasonic atomization occurs with very low liquid pressure and low flow rates. The atomization process is driven primarily by the frequency of vibration, not by turbulence or shear forces. Because of this frequency-controlled mechanism, ultrasonic nozzles generate very uniform droplet sizes. Higher ultrasonic frequencies produce smaller droplets, while lower frequencies generate larger droplets. For example, a nozzle operating around 120 kHz typically produces droplets on the order of tens of microns in diameter. Another key characteristic is the low velocity of the spray plume. Since droplets are formed directly at the vibrating surface rather than accelerated by compressed gas, the resulting mist travels slowly and gently toward the substrate. This allows precise deposition and reduces overspray, which is especially important for thin-film coatings and sensitive materials. The design also has practical advantages for industrial processes. Ultrasonic nozzles typically have no moving mechanical parts, and the continuous vibration tends to prevent buildup of material on the atomizing surface. This makes them inherently resistant to clogging, even when spraying particle suspensions or nanoparticle dispersions. To shape the spray for different processes, auxiliary airstreams or motion systems can direct the droplet plume into narrow lines, wide fans, or patterned coatings. These configurations allow ultrasonic spray to be used across applications such as semiconductor processing, fuel cells, medical devices, and advanced materials manufacturing. Ultrasonic spray technology has been refined and commercialized by companies such as Sono-Tek, which has developed specialized nozzles and coating systems based on this principle for research and production environments. At its core, however, the concept remains elegantly simple. Convert electrical energy into ultrasonic vibration. Use that vibration to create controlled capillary waves in a liquid film, and transform the liquid into a uniform cloud of precisely sized droplets.